Hello, my name is Richard Anthony Marca, and this is my project 4 for my CSC421 AI class. And today we actually have two parts for this project. One is for classification, and the other is for regression in these two Colab notebooks. So while I read out what each section is about, first, I'll show you the data I'm using for both of these, which is going to be for Pokemon. And besides the ID number, we also have the name, the first type, their second type, whereas if they do not have a second type, we list it as none. The total stats, or the base stat total, their HP or health points, their attack, defense, special attack, special defense, speed, and which generation they're in. And this goes all the way down to generation 9 at 1025 Pokemon. So now I will load and initialize the data, make sure it's good. I'm going to go through each block code and activate them step by step. This is to keep useful columns and adjust type 2. And this is to encode type 1 and type 2 and build the feature matrix for stats in type 2. And this is to split the training data and the test data. This is to scale the features. This is the first one for the logistic regression, where the logistic regression uses both stats and type 2 to accurately find type 1. If I run it, it's not very accurate because there are 18 type 1 classes, while there are 19 type 2 classes, because there is no none in type 1, it's only in type 2. So next is the KNN, or K nearest neighbor, whereas logistic regression is a linear model. K nearest neighbor classifies a Pokemon based off the type of its closest neighbors in the feature space. So for this one, I chose n neighbors equals 5 because it's a common balance between noise sensitivity and smoothness. So if I run this, you're going to see that the accuracy is actually going to be a little bit less than the logistic regression. So the third one I chose was random forest, where it is similar to decision trees, where it's great for handling nonlinear relationships and interactions between the stats. And for the estimators, I use 200 to give it enough trees for a stable prediction. So if I run this, and this one actually does a little bit worse than the K nearest neighbor. And lastly, we got the SVM with the RBF kernel, where SVM tries to find the best separating boundaries between classes. The RBF kernel allows it to model complex curved boundaries. So I used the default 1.0 for C and gamma as the scale. And so if I run this, well, it's even less accurate. Now let's run to confusion matrix to see how well each of these did in comparison. And because there's so many different types, it's not going to be very accurate. So here's the accuracy comparison table if I run this, with logistic regression being the most accurate out of the 4. So this is the result summary of the Pokemon type classification. And using these 4 different strategies, which were unique among themselves, with specific parameter choices like max iteration equals 1,000, n neighbors equals 5, n estimators equals 200, and c equals 1.0, and gamma equals scale. It showed that the best accuracy was with the logistic regression. And even though these values appear low, they are definitely well above random chance, which would be about 0.055 for over 18 classes. And since Pokemon typing is a high cardinality multi-class problems, and many types do share overlapping stat distributions. For example, water, ice, and psychic types often have similar stat profiles. And dual types like bug poison and grass poison are difficult to distinguish using stats alone. Where the best model is obviously going to be the logistic regression because it had the highest amount of accuracy, which suggests that the relationship between stats and type is not strongly nonlinear, and that more complex models don't gain an advantage without hyperparameter tuning. And with the more rare types like Dragon, Ice, and Ghost, the model struggled more with those. Even though the accuracy values were modest, it does show a bit better. And one of the things that I would probably do next time is maybe use just the first generation, because it seems like the first generation definitely has the more categorically unique compared to types. Also, maybe address class imbalance with class rates or synthetic minority oversampling techniques or smoke. Or I could try predicting the combined type as a single label, but that seems like it, again, because this is already bad, I feel like that would do worse. So that is it for the first project. So here is the second notebook, which is going to delve into the regression task. And it's going to be using the same Excel file as before, but for this regression tasks, I'm actually going to be doing something different. I'm going to try to predict a Pokemon's base stat total or BST value, which is a numeric target, based off of their health, attack, defense, special attack, special defense, speed, and I'm also going to hot code the type 1 and type 2, which gives the model a complete view of a Pokemon's stat distribution and typing. So let me start doing this. Connect to Google Drive. So let me start running these. So it is mounted. Now if I do the imports and the data, as you can see, here's the total. Similar to the one before, but this time we're going to have just the total in the name for the features and the total. So with some scalar features as well. There we go. So this time we are only going to use 3 regression models, which is going to be linear regression, the random forest regressor, and the k-nearest neighbor regressor. So let's start with the first one. Second. And third. Where the linear regression is a simple baseline model that assumes a linear relationship between the features and the target, which is a good starting point because total stats are almost the sum of the individual stats. Then we got the random forest regressor, which is a non-linear ensemble model that captures interactions between stats. And I'm going to be using n estimators at 200 for stability. And then the k-nearest neighbor regressor is a distance-based regression model where I use n neighbors at 5 for a more stable function. So let's evaluate the model. And as you can see, some of these results are kind of surprising and some are not. And I'll explain that in a second. So by predicting the base stat total, or BST, the linear regression is basically perfect because, well, it kind of is the total of the base stats is the total of all the stats combined, which should be linear. It should be a near zero error, and this result is expected because, as I said before, it's the sum of the individual stats, which should make the relationship perfectly linear. So, which also shows that the data was inserted correctly because there shouldn't be any margin of error. But if you look at the random forest regressor, that also did extremely well. While the k nearest neighbor did not do so hot. Still did better than what I did in the classification, but nowhere near linear regression or random forest. So the random forest regressor shows that it can approximate the linear relationship even without explicitly modeling linearity. And both the linear regression and random forest were close to perfect, with linear regression being perfect. The weaker k nearest neighbor model still captured a substantial portion of the variance, where k nearest neighbor struggled due to the curse of dimensionality and sensitivity to scaling. And next time, I'd probably perform, again, hyperparameter tuning, like maybe add max depth for random forest or adjust the k for k nearest neighbor. I could also try adding more features such as height, weight, or abilities. I could visualize feature importance to understand which stats contributes most to the total. And I could also explore predicting other numeric targets like capture rate, experience growth, or base happiness, because that's also a thing. And that is it for this project. Helped me learn multiple machine learning models for both classification and regression tasks. That is it for this video, and thank you for watching.